In this video, we're going to be talking about our prerequisite review for Math 261, Applied Calculus. This is the first of the videos in that series. We'll start off with a review of algebra and functions with a catalog of essential functions here. And the first one we'll talk about is a linear function. In the library of functions, a linear function is going to be the line y equals x. So it's going to look like this, the identity function, y equals x. The domain of this function is going to be negative infinity to infinity. The range of this function will also be negative infinity to infinity. Examples of this type of a function would be anything in the form of y equals mx plus b. So, like f of x is equal to x plus 2, or f of x is equal to a negative 2x plus 1. Something like that, where we have slope and we have a y-intercept here. We can also express a linear function in point-slope form. Y minus y1 is equal to m times 1 dx minus x1, where m is equal to y2 minus y1 over x2 minus x1. The slope is going to be our average rate of change. Later on, we'll talk about that. Okay. Next type of function we talked about is a second degree polynomial. This is first degree. And you're going to see that it's going to cross the x-axis only one time. Second degree could cross 2 times, but our y equals x squared that's in our library of functions here is going to have its vertex at the origin 0, 0. So it's going to be in the form of y equals ax squared plus bx plus c, or it could also be in the form of y equals x equals, a times x minus h squared plus k. It's going to have a vertex, like I said, at h, k, and a is going to be how much we are stretching this out. We can get from this form to this form by completing the square. We find the x-intercepts of this using the quadratic formula. We'll have a y-intercept at 0, c. And let's see, what else? Domain here, it's going to be negative infinity to infinity since it's a polynomial. And its range, if it opens up, a is greater than 0, is going to be k to infinity, closed at k. If a is less than 0, we're going to go from negative infinity to k, and the vertex will be a local and absolute max. More on that later. If a is less than 0, our vertex will be a local and absolute min. if a is greater than 0. Again, more on minima and maxima later. Our cubic function. Look like this, and we're going to have this turning point right here. It's going to be called a point of inflection because the concavity changes here. It's not the only type of point of inflection. It's one of the points of inflection where the graph is filling up with water here. Water is spilling off a bit later. Again, this is just an introduction to some things for later. So our domain is -infinity to infinity. Our range is also going to be -infinity to infinity, no matter which way it opens. End behavior will be going up and to the right. If our a is positive, this is going to be in the form of y equals a x cubed plus bx squared plus cx plus d. Every once in a while, I can complete the cube and get that into the form of a times x minus h cubed plus k. And write it in that transformation form. We'll talk about transformations here in just a second. If so, this point here will be hk. And examples of what this might look like would be f of x is equal to, if it's in this transformation form, it might look like that. Or f of x might look like x cubed plus 2x squared plus x minus 1, something like that. All right, now we've got some radical functions, functions that are involving roots. First one is going to be the square root of x. It's going to look like that. Let's put this in red since it's important. You cannot evaluate f of x equals the square root of x at negative values of x. Look at how there's only behavior to the right over here. There's no behavior to the left. I'm not allowed to have any negative x values. So whatever is underneath the square root sign must be greater than or equal to 0. So our domain here is 0 to infinity, and our range is also 0 to infinity, like that. Examples of what this may look like would be something like the square root of x minus 1, or f of x is equal to maybe the square root of x plus 2 minus 3. You'll see that I try and close off my square roots like that as much as I can to show you where they end. That's just a me thing. So that's not really part of the symbol, but I kind of treat that as the end of my parenthesis there. All right, we've also got cube roots. I don't have that here, but a cube root is going to look like this. Cube root, and it's also going to have a domain of negative infinity to infinity and a range of negative infinity to infinity. And again, you could have similar types of roots. Probably won't see many fourth root. And one for your class here is the reciprocal function. Here, we're going to use this a lot to talk about the idea of limits coming up here. So you're going to deal with a lot of rational functions and the limits here that come from the horizontal asymptote and the vertical asymptote. So we have a domain here. of negative infinity to 0, union 0 to infinity. Another way to say that is x cannot be equal to 0. We have a range of negative infinity to 0, union 0 to infinity. Another way to say that is y cannot be equal to 0. We have a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. Examples of what this may look like. Examples, f of x may be something like 1 over x plus 3, or we may get something like f of x equals 2 over x minus 2 to the 5th minus 7. This power here doesn't necessarily have to be 1, but this is an odd negative power on x. Will look something like this. If I have an even negative power on x, it's going to be based off of this graph, and it's going to look like this. I have a domain, negative infinity to 0, union 0 to infinity. My range here is going to be 0, not included, to infinity. And examples here would be things like 1 of y equals 1 over x squared plus 3, and y equals 1 over x plus 2 to the 4th plus 9. They'd be based off of those. Right? Another type of function we're going to talk about is going to be the exponential function. It's a rising curve like this. For f of x equals e to the x, my domain is going to be negative infinity to infinity. My range is going to be 0 to infinity. Watch out that I can have negative exponents. So if I have something like f of x equals e to the negative x, that's actually a falling curve like this. We could have something like f of x is equal to 2 to the x. Because that's greater than 1, it's going to be a rising curve like this. So y equals 0 is a horizontal asymptote. Right? One more function here before we get on to transformations of functions, and that is the logarithmic function. It has a characteristic point right here at 1, 0. This one had a characteristic point at 0, 1. My domain here is going to be 0, not included, to infinity. Range is going to be negative infinity to infinity. And we may have, like we have here, natural log, or we may have logs of other bases. So we may have something like f of x is equal to ln x minus 1, or f of x is equal to maybe log base 2 of x. Key note here, though, x equals 0 is a vertical asymptote. And also note here that f of x equals log base 10 of x is written as the common log of x. This is the same thing as log base e of x. So remember that the natural log is log base e related to this function up here. All right, transformations of functions. Recall for constants a, b, c, and d, and function f of x that we can write y equals a times f of quantity b times quantity x minus c, close parenthesis, plus d in our transformation form, where a scales the function vertically. A less than 0 is going to flip f of x over the x-axis. B scales the function horizontally, and b less than 0 flips f of x over the y-axis. C shifts f of x in the x direction left and right. A positive c value is going to move it right here, and negative c value will move it left. Notice the minus sign that's in the formula. So it's going to do the opposite of what it looks like in the formula because there's a minus sign. There's a positive sign here in front of d, so d shifts f of x in the y direction up and down, and it's going to do exactly what it looks like, that a positive d value will move it up and a negative d value will move it down. So just make a note here, x minus c shifts right c units, and x plus c shifts left c units. Okay. So let's use our transformations to sketch the graph of negative quantity x minus 1 squared plus 3. So that's going to be quadratic with a vertex at 1, 3. And it's going to open down. So our A is going to be -1, our B is going to be 1, C is going to be 3. Sorry, C is going to be 1, and D is going to be 3. If this is in the form of f of x is equal to A times B times x minus C plus D, like that. So we have no horizontal compression. We are reflected over the y-axis at x is 1, y is 3, x is 0, y is going to be 2. So we're going left 1, down 1 because of this A. We're going to go right 1, down 1 because of that A. And we get something that looks like this. Our new vertex here was at this HK here is at 1, 3. This told us to flip over the x-axis. This told us to go right 1 unit. And this told us to go up 3 units. This one did nothing. All right. Let's talk about inverse functions for a second. We did this in Precalculus as well. If we want to find the inverse of f of x is equal to 2 over x plus 1, slightly different wording of the process here, but same thing that you did in Precalculus. Instead of switching x and y in the beginning, I'm going to switch x and y at the end. So I'm going to solve for x here. When I replace this with y, y times x plus 1 equals 2. X, y plus y equals 2. Xy equals 2 minus y. And x equals 2 minus y over y. Like that. or you can write that as 2 over y minus 1. Same thing, split them up over the common denominator like that. So now we're going to call x f inverse of x, and we're going to make our y our x. This is our inverse step right here. And then we can confirm graphically that they are inverses of one another. If we take the original function here, just as an example of two things that are inverses, here's y equals e to the x. And here's the line y equals x. And here's the curve y equals ln of x, that every point, like this point 0, 1, will switch x and y values and will become a point over here like 1, 0. And note that you have this horizontal asymptote over here on this side that turns into this vertical asymptote down here when we switch x and y. All right, let's find the inverse of 2 log base 3 for x minus 1. I'll use the steps that you learned in Precalc instead of the steps the way they were listed up there. So first thing would be to replace f of x with y if you need to. Now we're going to switch x and y. Now we're going to solve for the new y. And then we're going to replace that y with f inverse of x. And we're done with that. Let's talk about compositions of functions. Important note here with compositions of functions and inverses. If I compose inverse functions, I have to always, all the time, get x. That's why we're talking about this one next. It's the way to prove that things are inverses. So what this is that I take, there's an outer function and an inner function. This will be very important in calculus to be able to identify outer and inner functions when functions are composed like this. And so I'm going to put the inner function in the place of the variable in the outer function. So g is my inner function, and it's going to replace my variable in my outer function. So I'm going to write my outer function down without my variable. In place of my variable, I'm going to write my inner function down. Then I'm going to go ahead and expand. So this is x plus 2 times x plus 2 plus 1. Do not just say this is x squared plus 4. That's bad. Don't do that. You're going to miss your middle term. Don't forget to FOIL here. X times x is x squared. And then your O is going to give you a 2x, and your I is going to give you another 2x, and 2 times 2 is 4. Plus 1 is going to be x squared plus 4x plus 5. Let's try this one here, where we want f of g of x. So f of g of x is going to be f of x squared plus 1 square root of x squared plus 1 plus 2 is square root of x squared plus 3. And that's it. We can't split that up anymore. Note that if we went the other way and did g of f of x, that this would be something squared plus 1. This would be the square root of x plus 2. And when I square that square root, it would go away. I do want you to just note something right here. It's going to be important later on in the class, possibly, that the square root of x squared is equal to the absolute value of x. It's not equal to just x. This is one of the definitions for the absolute value of x. All right, rules of exponents and logarithms. Just remember that when you multiply like bases, you add the exponents. When you divide like bases, you subtract the exponents. When you raise a power to a power, you multiply the exponents. You can write negative exponents as positive exponents in the denominator. When you see a negative exponent, bring it across the fraction bar and change sign. When you see roots, you can write inside power divided by index for the root. Remember that when you see no index, it's going to be 1/2 here. Nothing on the inside is a 1, nothing written on the outside is a 2 of the root there. So when I just see something that looks like the square root of x, that's x to the 1/2 power. So another example here is if I have the cube root of x to the 4th, that's going to be x to the 4/3. Let's go ahead and simplify this expression just for practice. X squared times yz over xyz to the 4th, all raised to the 3rd power. So we're going to make this x squared times y times z over, and when I raise a power to a power, I'm going to multiply the exponents. So this is x to the 3rd times y to the 3rd times z to the 12th. Let's try and write this with only positive exponents. So subtract the smaller number from the bigger number and leave the variable where the bigger power was. So 3 minus 2 is 1, and that's going to be in the denominator. 3 minus 1 is going to be 2 in the denominator. 12 minus 1 is going to be 11 in the denominator. And I have an invisible 1 left over in the top. Now, related to laws of exponents are laws of logarithms. So if I have log base a of x equals y, that's an equal sign, it's a poorly written equal sign, equals y, then I have that can be written as a to the y is equal to x. If the bases match each other, they're inverse functions and will undo one another for all values of x. Same thing here. These are inverse functions and will undo one another, but I have to obey the domain of that inner function, so x has to be greater than 0 here. When I multiply on the inside of a log, it's addition of logs. So this goes back to the when I multiply like bases, I add the exponents. The logarithms are the exponents. So when I multiply in like bases, I add the exponents. When I divide like bases, I subtract the exponents. This is a power here. So when I raise a power to a power, the power can be written on the outside as well, like this. I'm going to multiply the exponents. Note here, very important note, that log base a of x to the r is not the same thing as log base a of x raised to the r. Here, x is being raised to the r. Here, the whole log is being raised CR. Be very careful with your notation there. So, all right, that's it for your pre-calculus review. And we will come back next time and start talking about the idea of limits. See you for the next video.